So Faraday's law, so basic law that discovered through experiments, and it was discovered by Michael Faraday around 1830. And the law tells us about electromagnetics inductions, the underlying principles of conversions of mechanical energy into electrical energy. Okay, so that is your generator. So without the discovery of Faraday's law, we will not have electricity today. Okay, so the basic principle behind generation of electrical energy is actually through Faraday's law. And then the transformer and also electromagnetic wave propagation, also the other two important examples of Faraday's law or electromagnetic inductions. Okay, so your electromagnetic wave propagations, that is the underlying principle of your mobile phone and all the things that related to that. So fundamentally, it links the electric and magnetic force. So electrostatic, we talk about electric force, and then magnetostatic, we talk about magnetic force. And this Faraday's law bring the two together. Okay, so before the discovery by Michael Faraday, these two believed to be two separate forces. They are independent of each other. And with his discovery, the two now are linked. Okay, the definitions of Faraday's law. So consider electric circuits that has a total flux linkage. The flux which can be produced either by current flowing through the circuits due to an external circuit or nearby magnets. So it can be three different scenarios. And Faraday's law states that the voltage V developed across the circuits equals to minus the rate of change of the circuit flux linkage. Okay, V equals to minus d phi by dt. So if I have a circuit, so this is my circuit. If I have a flux, then the voltage develops across that circuit depends on the rate of change of that flux. Okay, minus the rate of change of that flux, minus d phi by dt. So we write the induced current voltage V as a small letter to indicate that it is time dependent. So our V function of time, we write them as a small letter V. Okay, so to differentiate it from your DC voltage V. The minus sign in equation 11 can be explained by something known as a Lenz's law. The Lenz's law states that the directions of the electric currents induced in the conductors by a change of magnetic flux is such that the magnetic flux created by the induced current oppose change in the initial magnetic field. So it's trying to oppose the original magnetic field. Okay, so that's why it has a minus sign there. So we note that any time-dependent flux trading a circuit gives rise to a voltage across the circuits, and that is what Faraday's discovered. And there is no proof to that equation, and it's a fundamental law of nature, just like your Coulomb's and Biot-Stafford law, and they are determined through experiment. Okay, so consider a simple circuit like this. We have a voltage connected across the inductors. So I'm sure you know how to analyze this circuit. So we have V, which is changes with time. We have an inductors. So these inductors can be either a solenoid or a long transmission line structure. So you have an inductors which is have an inductance equals to phi over I. And then the current flow in the circuit is I. The voltage is V sub S, okay, indicating that is the supply voltage. So if we neglect the resistance of the inductance, so just ideal conditions, but in practice all inductance have resistance because inductance is made up of a very long wire in a coil. But for simplicity, we neglect the resistance and then we will try to analyze these circuits. Okay, so the voltage developed across the inductors, we know that VL equals to minus d phi by dt, and that is equals to minus di by dt. Okay, I'm sure you know this equation. V equals to L di by dt. That's the voltage developed across the inductance. So just now our circuits, we have our Vs, and then we have our currents here, I. So if we apply Kirchhoff law, okay, your Kirchhoff voltage law across this loop, then we can write that if this is my voltage, VL, okay, the voltage developed across the inductors, then if I sum the voltage across the loop, then Vs plus VL has to be equals to 0. And then from here, we said that Vs will be equals to minus VL, and our VL is equals to minus L di by dt. Therefore, we said that Vs will be equals to L di by dt. So the supply voltage vary with time. So we can write the time dependence as Ej omega. Okay, we know that Ej theta is equals to cos theta plus J sine theta. Okay, so we know that J theta is a sinusoidal. Therefore, we can write our time dependence Vs equals to V naught. V naught is just some constants times a time dependence parameters, which is Ej omega t. And with that, we can derive our impedance of the inductors, which is Vs, the supply voltage, divided by current. That's Ohm's law. V equals to IR. So R will be equals to V over I. And therefore, our impedance ZL equals to the supply voltage divided by the current, and that will be equals to J omega L. Okay, so just now we write that our Vs equals to V naught E J omega T, and that's our, and that is equals to L di by dt. Therefore, we can work out I. Di by dt will be equals to V naught over L E J omega t, and therefore I will be V naught over L integral E J omega t dt. So my I will be equals to V naught over L E J omega t divided by J omega t. Sorry, J omega. And our Vs and then our impedance ZL equals to Vs over I. That will be V naught E J omega t over V naught E J omega t over J omega L. And this cancels out, and therefore this is equal to J omega L. Okay, so that is how your impedance of your inductors come from. I'm sure you know that the impedance of an inductor is equal to J omega L. And the impedance of capacitance, do you remember what that equals to? 1 over J omega C. So what this tells you is that the current lags the voltage by a phase difference of 90 degrees. Why 90 degrees? Because it has a J there. Mutual inductance between circuits. Suppose that some time-varying current I1 in circuits cause a total flux linkage I2 in the adjacent circuit, which has no power supply connected to it. So we have a current I1 that generates a flux that links to circuits 2. We call that phi 2. And because if this flux varies, okay, changes with time, then we have a voltage developed across circuits 2. We have a V2. Okay, So V equals to minus d phi by dt. So if phi changes with time, then d phi by dt will be finite, and then we have a voltage developed. And earlier on, when we look at mutual inductance, d phi 2 by dt, that will be equals to m di1 by dt. And the current I1 is due to the changes in the current in circuit 1. So meaning that if I have a current that is changing in circuit 1, that will give rise to the flux changes in circuits 2. And because that flux changes with time, we have a voltage developed across circuits 2. And between these two circuits, there is a mutual inductance M. Okay, so the voltage V2 will be equal to minus M di1 by dt. This is the principle of how your transformer work. Okay, so your transformer so this is your circuit 1 that have a current I1. So this current I1 changes is caused a flux around the core of the transformer, and this flux changes give rise to a voltage induced at the other side of your transformer. Okay, so that is the principle of this. So changes the number of turns that change M, change the materials of the transformer core that also change M. Okay, so change the mutual inductance between the two circuits. Magnetic energy. So we consider the magnetic energy associated with a finite magnetic flux density in a region of space. So this is analogous with the electric store energy that we studied in electrostatics. So electrostatic, we study about electric energy stored, and here we have something similar, which is the magnetic energy. So in electrostatic, it will be stored in a capacitor. So here it will be stored in an inductor. Okay, so magnetic energy is stored in the inductor. So the magnetic energy is stored by a current carrying inductor. So if we have an inductor circuit like this, so the inductors have a self-inductance L, suddenly connects to a DC power supply, and then current will start to flow from 0 to I. Okay, so because your inductors is just a coil of wire. Okay, so when you suddenly turn on the circuit, the current will go from 0, eventually it will reach a steady state current I, which is your DC current. So just like our capacitor, we're looking at from 0 charge to Q charge. Here we're looking at from 0 currents to I current, from the initial conditions to the current I. So again, we neglect the resistance in the circuits just to make things simpler. So the power is equal to current times the induced voltage, P equals to IV, and the voltage induced in the inductors is equal to L di by dt, and the current is the current flow in the circuit. So the total work done will be integrating the power against time, and then we'll be integrating from I equals to 0 initial state all the way to where I becomes the DC current I on the circuit. Okay, so your power is I, L di by dt, integrated over time. So dt and dt cancel out, and we end up with L is a constant. We take it out from the integral from 0 to I, L dt. Okay, so this integral, so integrating, sorry, it's not dt, it's di. Okay, so integrate I di, that will be I squared over 2 over the limit 0 to I, 0 I. Okay, and that gives you your I squared over 2 and then you have the L constant, so it's half Li squared, and that is the power done by the power supply to create the currents to flow from 0 to I. Okay, conservation of energy, the work done by the power supply has to be equals to the magnetic energy stored in the inductors. So the power supply used this much or does this much work to charge up the, or it's not the right term to call it charge, to induce the inductor. Okay, so that energy has to be stored in the inductors, and therefore the energy stored in the inductors will be equals to half Li squared. Still remember what's the energy stored in capacitor? Half CV squared. Okay, so you can see the similarity between the two from the capacitor and the inductor. So this whole topic talking about electric charge and the magnetic field, there are similarity between them. Okay, so just like our electric energy density, we can do the same for magnetic. Again, we defined something called a magnetic energy density. So the energy stored in the current carrying inductors is confined to those parts of the inductors where the magnetic flux density is non-zero. Okay, so just like your capacitor, okay, so your capacitor, the electric, we said, is stored within that volume of that capacitor structure. Similarly, we have our inductors. So if I have our inductors, so we have to set that the magnetic field also stored within this volume of the inductor. Okay, so we can define energy density related to magnetic. Okay, just to illustrate, so a long current carrying solenoid, the inductance is mu naught n squared A times L, and the magnetic flux inside that, or the magnetic flux density inside that solenoid is mu naught n times L. And therefore we can write our magnetic or store magnetic energy equals to half over or 1 over 2 mu naught times the magnetic flux density squared. And then this is the volume, and therefore we can write that our magnetic store energy equals to Bi squared over 2 mu naught times the volume of the solenoid. Okay, so A times L is the volume of the solenoid. So something like this. So this is my A, and this is the L of the solenoid. Okay, so the magnetic flux density inside that solenoid squared divided by 2 mu naught times the volume is also equals to the stored magnetic energy, and therefore we can define the magnetic energy density as B squared over 2 mu naught. Okay, so just now we have U equals to Bi squared over 2 mu naught times the volume, and then if we divide that, that will be equals to Bi squared over 2 mu naught, and we define this as the energy density. Okay, so for any structure, you can work out the energy density by working out the magnetic flux density inside that stored components divided by 2 mu naught, and then if you multiply that by the volume, then you can find out how much magnetic energy can be stored in that particular structure. Okay, so the magnetic stored energy is a scalar quantity, has a unit of joules per meter squared, per meter cube. So if the region of space has a volume V and the field is uniform, then the total stored energy will be the energy density multiplied by the volume. Okay, so the magnetic energy density is B squared over 2 mu naught, so times the volume give you the total stored energy. And if the magnetic flux density is not uniform over that volume, then you have to integrate it over that volume. Okay, that will be B squared over 2 mu naught dV, integrating over the volume V. Okay, so we have something similar for the electric energy, and then this is the equivalence of that in the magnetic energy. Okay, here's an example. The solenoid has a radius R1 equals to 1 centimeters. A total number of turns per meter N1 is equals to 2000 per meter, and the length L1 equals to 50 centimeter. And then we have a smaller solenoid, has a radius of 0.5 centimeters, and then has a turn per meters of 500 or 5000 per meters and length of 10 centimeters. And then this smaller solenoid is placed deep inside the larger solenoids. So this question asks you to work out the mutual inductance between them. Okay, so this one has a length L1, and this has a length L2. And then the number of turns of the circuits here, you have N1, which is 2000 per meter. So the number of turns N1, if you're interested to work out, that will be N1 times L1. And then N2 will be N2 times L2. If you want to work out the actual number of turns in the circuit or in the solenoid. If you assume current I1 flow in the outer solenoids that produce a uniform magnetic flux density along the axis of the inner solenoids of magnitude B equals to mu naught N1 times I1. Okay, so we know that the magnetic flux produced in a solenoid is equals to mu naught N times L. The flux trading each turns of the smaller solenoids will be phi 2 equals to B pi R2 squared, and then the flux linkage capital Phi will be N2 L2 times the flux, and that gives you mu naught N1 N2 pi R2 squared L2 times I1. In case once you know the flux, then you can, or the flux linkage, then you can work out the mutual inductance. Or similarly for self-inductance as well. Okay, that will be equals to the flux divided by the current. Okay, so the mutual inductance between the solenoids will be equals to phi 2 flux linkage in the smaller solenoids divided by the currents that flow in the larger solenoids. And that will be equals to mu naught N1 N2 pi R2 squared times L2. And in that particular example, it works out to be 99 microhenry. Backtrack to this discussion. So we have the large solenoids have current flow I1, and that generates the flux, a magnetic field inside here B, that is given by this equation. Okay, mu naught N1 times the current I, and then that field creates a flux phi 1 in the smaller solenoid, and so that flux is over a single turn of the solenoids. Okay, and then we can calculate the flux linkage. That will be over the total number of turns over that solenoid. Okay, so your flux linkage phi is equals to n number of turns times the flux, and then N2 is equals to N2 times L2. Okay, so you're given N2 as per meter, the number of turns per unit length, and you're given the length of the smaller solenoids. Okay, so this is equals to N2 times phi 2. So putting in the value of phi 2 and then putting in the value of B, which is here, and that gives you this long equations here. And then the mutual inductance simply equals to the flux linkage divided by the current. Okay, and that will give you this equation. Another example. So in the previous example, the outer solenoid carries a current of 0.1 ampere at 10 kilohertz, whilst the voltage developed across the inner solenoid. Okay, so if the outer current is changing with time, we can write that I equals to I naught, which is the maximum amplitude, changes with time, that is E j omega t. And then we know that omega is equals to 2 pi f, and then she given the frequency as 10 kilohertz. Okay, so this is f. And you can work out omega is equals to 2 pi f. Okay, I naught is given as 0.1 ampere. And then mutual inductance in the previous example is 99 microhenry. The flux linkage of the outer solenoids is equals to phi 2 m I1 equals to m I naught. So this is my I1, which is this equation here. Okay, so I1 is here, I1. Okay, substituting I1. And then the voltage developed across it will be minus d phi 2 by dt. And that will be equals to minus j omega m times I1. Okay, so this gives you the induced voltage across the inner solenoids V2 to the driving currents I1 that passes through the outer solenoids. Okay, if you plot the currents and the voltage, this is how it looks like. You can see that there are 90 degrees between them in phase. Okay, so that is your voltage and current. So find the inductance L for a solenoid using the concept of magnetic energy density. So this is something similar that we have done for capacitor in electrostatics. So this is simply working backwards the above discussion. So we assume B is uniform inside solenoids and zero outside. Hence we have, so the magnetic stored energy density is B squared over 2 mu naught. V is the volume. And we know that the magnetic flux density is mu naught N times L, square that, times L times A, which is the volume of the solenoids. And equate that to half L di by dt, and you can work out that the inductance equals to mu naught N squared A times L. Okay, so this is the self-inductance of a solenoid. More example. So 10 volt DC supply connected across a length of parallel plate transmission line and terminated with 50 ohm resistance. The plate width is 1 centimeters and the plate separation is 0.5 millimeters. The space between the plate is filled completely with a dielectrics of relative permittivity 2.0. And then find the electric energy density between the plate, the magnetic energy density between the plate, and the total stored energy per unit length of the transmission line. So this brings together the things that you studied in electrostatics and the magnetostatics. Okay, so we have a parallel plate transmission line. One side connect to a supply, the other side connected to a load. So here you have a current. At the same time, you also have charge between the plates. Okay, so you can work out the electric energy density between the plate, and you can work out the magnetic density between the plates, and then work out the total stored energy of the plate. So we have 100 watts here, 50 ohms the other end. Width is 1 centimeter. Separations 0.5 millimeter. Epsilon r equals to 2.0. So that is the questions to solve this. So looking at the width, so assuming that this is my transmission line going in this direction, this will be L in this direction. So there will be a current flowing. So in this example, current flowing in this direction and then going in back at the bottom plate. And then you have positive charge on the top, negative charge at the bottom. So you have electric field going from the top plates to the bottom plates. And then you have the current flowing. Then you have magnetic flux going between the plate. Okay, so the electric field between the plates is equals to the voltage divided by the separations. That will be 2 times 10 to the 5 watts per meter. The electric energy density between the plates. Okay, so that is equals to half epsilon naught epsilon r e squared, or okay, half d times e, and d is equals to epsilon r epsilon naught e, and therefore we get half epsilon r epsilon naught e squared. And we can work out e, which is v divided by d, and that is 2 times 10 to the 5. Okay, v is given as 100 watts, d is given as 0.5 millimeter. And therefore you can easily calculate the electric energy density, and that will be equal to 0.354 joules per meter cube. Okay, the current flowing along each of the plates, we got a voltage of 100 watts, and we got a load at the other end, which is 50 ohms. Okay, so our transmission line, something like this. We have 100 watts here, and then we have 50 ohms at the other side. Okay, therefore the current I will be equals to V over R. And then the magnetic flux density of a parallel plate B will be equals to mu naught I over W. And I is V over R. Put those parameters in, that give you 2.51 times 10 to the power minus 4 Tesla. And the magnetic energy density, which is B squared over 2 mu naught, and this gives you 0.0251 joules per meter cube. Okay, so this is actually okay, B equals to mu naught H. So the magnetic energy density is half H times B, and your electric energy density is half D times E. Okay, you can see the parallel of the two, and therefore you can calculate the magnetic energy of the parallel plate, which is B squared over 2 mu naught, and that gives you 0.0251 joules per meter cube. So taking a 1 meter length of the transmission line, the volume of the plate equals to 5 times 10 to the minus 6 meter cube. So the energy the total stored energy in both field per unit length will be the 2. So this is my UE, this is my UM, okay, times the volume. So this is my volume, and that gives you 1.9 times 10 to the minus 6 joules per meter. So for every 1 meter length of my parallel plate, it stores a total energy of 1.6 times 10 to the minus 6 joules. Okay, so that's an example that brings together the electrostatic and the magnetostatics that we have studied. Okay, another example, superconducting solenoids of a medical MRI. Machines has a diameter of 1 meter, a length of 2 meters. You know what's MRI? Magnetic resonance imaging. Okay, the things you use in hospital, you put a person into it. So this alternative to your X-ray. So it's generated through magnetic resonance. So you can ignore what superconducting, just solenoids. Okay, so that create a high magnetic flux. So it provides an axial magnetic flux density at the midpoints of 0.5 Tesla. Estimate the magnetic energy stored within it, and also estimate the magnetic energy stored within a typical human body. Okay, assume mass of 70 kilogram when it's being scanned. Okay, so this is the example. You have solenoids creates a midpoint magnetic flux density B of about 0.5 Tesla, and then it has a diameter 1 meter, a length of 2 meters. So we still assume that it's uniform flux density across this, okay, to make things easier. So UM equals to B squared over 2 mu naught. B is given as 0.5 Tesla. Volume of the solenoids or the coil is pi times 0.5 squared, and then the length is 2 meters. That gives you 1.57 meter cube. The magnetic energy stored within it therefore equals to UM times V, and that gives you 4.91 times 10 to the 5 joules. Okay, so this is 1 meter, this is 2 meter, and then we assume that the magnetic flux uniform at 0.5 Tesla, and therefore the magnetic flux density within this solenoids is B squared over 2 mu naught, and that gives you 3.13 times 10 to the 5 joules per meter cube. And this volume has a volume of 1.57 meter cube, and therefore the magnetic stored energy is roughly about 4.9 times 10 to the 5 joules. So typical human body is about, let's say, about 70 kilogram, and assume that the mass density is 1 kilogram per meter cube, and that gives you a volume or typical volume of humans of about 0.7 meter cube. And then the magnetic energy stored within the human body when placed in the solenoids, that will be the magnetic energy density times the human's body volume, and that gives you about 2.2 times 10 to the 7 joules.